All right, howdy everyone. My name is Carl Runko from the VFS Arizona chapter out here. Thanks for coming to our technical talk, virtual tech talk here. We hold these occasionally just to introduce our members to the broader field of aerospace and, well, the more specific field of vertical flight. Keep the members appraised with the up-to-date research and what's happening in the field. So we hope you enjoy our speaker today, who is Jason Cornelius. As for our chapter events, please check out our chapter page. Shoot, I don't have that URL now. I will be better at this in the future, but um, we do have a chapter page. Feel free to check that out. We will be having some upcoming events with a local helicopter company, a little air show we'll be volunteering at, and we do stuff with the local school. So if you'd like to get involved, check us out. And we have some other chapters here also joining us. Dan Jepp is president of the Redstone chapter, I believe, but I'll turn it over to him and he can give his announcements. So Dan, take it away.
Thank you very much, Carl. One correction, I'm the president of the Philadelphia chapter.
My bad.
No worries. Still very happy to be here and very grateful for the opportunity to give some updates. We don't have too many chapter specific updates for the Philadelphia chapter right now, but I do want to call everyone's attention to the Licton competition, which is starting to heat back up for this year. If people aren't familiar, the Licton Award was established to provide an incentive to VFS members who have not previously presented the results of their work and research at a technical forum or conference, and to just kind of get their foot in the door and help them with getting started and presenting at things. If anyone or anyone on the call they may know is interested, it starts with local chapter competitions first. So reach out to your local chapter and see if they're holding a competition, and if so, how you can participate. It's a great opportunity. If you end up winning the grand prize, you'll get travel funds to the forum this year. That's scheduled for May 20th to 22nd in 2025 for in Virginia Beach, Virginia. You also get forum registration and lodging. Overall, great opportunity. With that, I will pass it off to the next speaker from the San Francisco Bay chapter, Stephen Wright.
Hey everyone, glad to be here. My name is Stephen Wright, and I'm currently the president of the San Francisco Bay Area chapter of the Vertical Flight Society. Glad to be here to give a couple announcements from our chapter. Not too much to talk about. We just transitioned over to our new board, so that's one of the big things that's happened for us recently. We have a technical seminar coming up on October 9th that we'll be sharing the link with your chapters for that. So free to call into that. It's going to be Professor Sven Schmitz from the Pennsylvania State University. He'll be giving a presentation titled A Renaissance of Aerodynamics, Revise and Surpass Classical Theory with Modern Computational Methods. So that's much like today's talk. There's going to be a hybrid component, so people can call into that no matter what chapter you're in, and we'll make sure that you all get the invite for that. But again, that's October 9th. And that's about all I've got from our chapter.
All right, wonderful. Thank you, Stephen and Dan. I see our wonderful coordinator, Betty, is putting the links to the chapters in chat, so you can find more information there. I did forget to mention that we have a transformative vertical flight conference coming up in the Phoenix area, and abstracts for that are due the 14th. I know it's a little bit of a last minute notice, but if you have something you want to submit, or if you're currently working on one and you haven't submitted yet, go ahead and get that in. And otherwise, we will get the show on the road and allow Jason here to give his presentation. So the talk will be about an hour, well, 30 to 40 minutes, however long Jason's planned. And then at the end, we will have questions. So if you want to ask a question, if you have a question you want to ask, you can put it in the chat and we will get to your questions at the end. You can type it in, or if you prefer, we can unmute you, raise your hand, and we'll unmute you at the end, and you can ask your question directly. So With that out of the way, I'll present Dr. Jason Cornelius. He is from the NASA Ames Research Center. He's an aerospace engineer in the aeromechanics office at NASA Ames. His research interests are in rotorcraft design optimization with machine learning. He currently supports the RVLT project and Dragonfly and is the PI for the Digital Transformation Prototype Project, multi-fidelity machine learning-based surrogate models for terrestrial and planetary aerial vehicles. All right, Jason, the floor is yours.
All right, Carl. Well, thank you very much for the introduction, and very excited to be talking with all the chapters today. You know, I actually have personal ties to, I think, everyone involved here. So Philadelphia is my home chapter. We'll be getting back there pretty soon, actually, to the East Coast. So I'm excited about that. Of course, now over at Ames Research Center, so San Francisco Bay Area chapter. And then I was actually, in Mesa for the VFS TV. I guess it was the Mesa meeting just about a year or so ago, or I guess maybe now almost 2 years ago. But anyway, I'm very excited to be here. So thanks everyone for joining in. And today I'll be giving the forum presentation that I had done this past May in Montreal. But first, I have a video for you guys about Dragonfly. So let me share that first, and then we will jump over to the PowerPoint slides. All right, and if I could just get let's see, I actually have it pulled up here so I could see what you guys are seeing. And I hope this audio comes through. Let's try it out. All right, awesome. So that is by far the most interesting part of this presentation. Now you guys have to listen to me for 25 minutes, but hopefully that's all right. Let me see if I pull this up here. I'm actually going to turn off my camera for now, and then we'll see if we can get this one full screen for you. Okay, excellent. All right, so the video I just showed, of course, was Dragonfly. And I'll tell you a little bit more of what exactly that is. But you can see a graphic of it here on the center of the screen as well. So, of course, you guys see, or you heard, my name is Jason Cornelius. My co-author on this paper was Professor Sven Schmitz from the Pennsylvania State University, where I did my PhD. And the title is Dragonfly Rotor Optimization Using Machine Learning Applied to an Overflow-Generated Airfoil Database. So I'll go ahead and jump right into it. And I'll try to keep things kind of brief today. And then we'll have plenty of time at the end for any questions or discussion. If there's follow-on interest there, I'm happy to go further into detail on any of the topics. So here's a bit of an outline of what I'll talk through. Just a bit of introduction in the beginning for what exactly is Dragonfly and what the mission is about. And then some motivation for the project today, and specifically what I will be focusing on, which is C81 table generation and the rotor optimization. I'll go into a little bit of background just to give a high-level overview of the types of machine learning and surrogate modeling topics that I'll be discussing, and then some methodology in that CD1 table generation and something that is called the Overflow Machine Learning Airfoil Performance Database. I'll go a bit into the optimization framework that was used in this work, and then show some preliminary results and touch on some summary and conclusions, and that's really pretty much it. So jumping right into it here. This is kind of an overview of the New Frontiers Dragonfly mission. Now, Dragonfly is the fourth of such New Frontiers missions that NASA has funded. The previous one, or one of the previous ones, was the Parker Solar Probe. That was basically a probe that was actually sent closer and closer to the sun on consecutive orbits, essentially. And so Dragonfly at least was about a $1 billion funding level, so it's quite a large mission. And you can see kind of the rendering on the bottom left, which is of course similar to what you just saw in that video. And then on the right side, we actually have some images that were taken on Titan. So we have been in Titan before, the Cassini-Huygens probe, and so Huygens lander probe and the Cassini orbiter have been to the Titan system in around 2005. And so those were sent there. You can see a rendering of the lander probe on the top right, which took the image that you actually see here on the left. Now, this composite on the bottom right there of that sketch is from the Cassini orbiter. That's a composite image of of Titan, Saturn's largest moon. And then a couple of fun facts here on the left side. So a few challenges that we face in designing a rotorcraft for Titan. One of them being the temperature. It's 95 degrees Kelvin, so it's a cryogenic atmosphere, and it's mostly nitrogen, but there's also methane. So interestingly enough, Titan has something very similar to Earth's water cycle, except that on Titan it's actually a methane cycle. So there are rivers and lakes of methane that then evaporate, form clouds, condense, and rain liquid methane. And so as you can imagine, it's a pretty hostile environment to design something for. The gravity is lower, however, compared to Earth, and the atmospheric density is much higher. And so when you combine the two of these, it means that we could fly pretty, I wouldn't say easily, but you can lift much more mass for the same kind of setup as compared to what you would be able to do on Earth. And so that really pushed the design of this, aircraft, or however you want to call it, towards a rotorcraft concept that would be able to do multiple mission hops around the planet, around the moon, to explore geographically diverse portions of the moon. And so I will show a little bit later what those hops look like, and we'll get to that in just a few slides here. So a little bit more heavily on the rotorcraft analysis side, let's talk about CD1 table generation. Now, for folks, if anyone's not familiar with that, right, CD1 tables are basically an airfoil lookup table. And so if we're going to do rotor conceptual design, which could be using a variety of different tools, right? We could have some kind of BEMT model or an actuator disk implementation, which could be standalone. It could also be set inside of a CFD flow field for the kind of rotor inflow and wake tracking and things like this. Just a few tools that come to mind, CAMRAD, RCAS, Flight Lab, many of these tools, right? Charm, these are all able to use something called CD1 airfoil performance tables, which are just a text file basically of airfoil, two-dimensional airfoil performance as a function of the angle of attack and Mach number. So now the issue with these, right, are that if you're doing something like conceptual design or design optimization, it's really computationally expensive to use higher fidelity data in these CD1 tables, such as maybe airfoil performance data generated using a CFD tool like Arc2D or Overflow. And so even though they're two-dimensional CFD simulations, if you're still having to regenerate them for every single iteration or perturbation of your rotor optimization, that can be a very, very computationally intensive task. And so what's usually done is that we usually see lower fidelity data used, or maybe higher fidelity data, but at the incorrect Reynolds and Mach number. And so you're really kind of taking some pretty significant assumptions here and not representing that rotor performance as accurately as you could be. So the takeaway of that are that these mid-fidelity rotorcraft optimization methods are still too computationally expensive for users without access to high-performance computing. And even some of the recent state-of-the-art studies with access to some of the largest supercomputers that we have still can require on the order of 2 or 3 weeks to do one of these optimization loops if you're using that higher fidelity input data. So the alternative, of course, you could simplify the problem. You could do a single rotor or a single condition or simplified aerodynamics, such as a lower fidelity airfoil representation. And we do see that, but as I mentioned, right, we miss out then on some of the accuracy and potentially miss something that will come up later and cause us to kind of go back to the starting point anyway. So the objective here today is to present something called the Overflow Machine Learning Airfoil Performance Database and characterize the accuracy of this using surrogate models for predicting that airfoil performance. So as you'll see, this is sort of aimed to be a replacement to doing that CFD in the loop and allows us to do design optimization at a much reduced computational cost. And then looking at actually basically doing that, I'll show how you can take that PALMO database and plug it into what I've used here as a Bayesian optimization framework for very efficient rotor design optimization. So we'll take a look at this in this novel framework in the context of the Dragonfly rotor system, and looking at 15 input variables for that rotor design and analyzing it for a Dragonfly 4-rotor setup. So that's one side of the vehicle. It's a coaxial quad rotor vehicle. And then looking at this over the anticipated Titan mission. So let's just jump into a little bit of background here on a few different topics before we really get into kind of the problem setup. The first slide here I have for background is the supervised machine learning approaches. And so really what we're trying to do here is take a lot of computational data and then make a reduced order model that we can query very, very efficiently and very quickly. And so you see two examples on the right side here. The top one is Gaussian process regression. And so you can kind of see that there are a few of these points along the graph that are actual data points that could be either computational or experimental. And then the GPR model is looking at how you can fit basically a line through those points, right, with some kind of equation. And then by doing that in many, many different ways, you can simultaneously get a prediction for in between your data points, so you can interpolate, and you also at the same time get a prediction of uncertainty for those interpolated points. So it's a really good approach for basically data upscaling or interpolation and things like this. Some of the caveats, however, it's actually a good thing. It's really good for small data sets, and it captures that model uncertainty, like I mentioned, which is great. But the really kind of big drawback is that it scales poorly with more data. So as your data set gets bigger, the computational expense to build these models goes up with the data cubed, the size of your data set cubed. And so it becomes pretty intractable for a larger data set. There are more advanced methods such as sparse GPRs and things like that, but kind of the basic GPR faces this issue. Now for the neural network on the bottom right, this is kind of the idea where it's really mapped after kind of how the brain is set up with different neurons and things like that, and how they're all interconnected. And so the basic idea of this, or maybe some of the pros and cons, right? It's inexpensive to evaluate. So once you have it, it's very, very fast and very lightweight. It can handle very complex and high dimensionality data very well, but kind of a con or a drawback, it's data hungry. So a neural network using a very small data set will maybe not perform as well as that GPR, but then it scales better. So as you get more and more data, the neural network may actually become kind of the winner there. So anyway, these are kind of the two main methods that we usually see, especially in aerospace applications, I would say. And it kind of depends what your specific application is to whether one would be better than the other. In this particular study, you'll see that the GPR is actually used in the optimization because that's part of that Bayesian framework, whereas the neural network is used for the PALMO surrogate models of the airfoil performance. So a little bit of mixing and matching some of the different approaches here. So kind of one takeaway bullet at the bottom. Right now, over the last, I would say, year to 2 years, I've been personally investing in this machine learning just due to its promise for efficient and accurate database upscaling. So I started using these approaches on Dragonfly when I was in the kind of tail end of my PhD, and then figuring out how this could be translated and applied to other problems within aerospace, and of course, not just Dragonfly, but much further beyond that. So let's talk about the airfoil surrogate modeling for just a minute or two here. This one is really kind of, this is a pretty active area of research, actually. So there are many groups around the country and even around the world that are using those machine learning methods to do exactly what I described. So they generate some database of airfoil performance, and then they use these surrogate models to train a reduced order representation on that data, which they can then use to predict new conditions that weren't run or weren't tested in the experimental or computational data sets. Or you could actually use it to basically estimate performance for a new airfoil. There are also groups that are looking at how you can specify your desired performance. So you could say, I want this lift to drag ratio and this type of pitching moment characteristic, and then it will actually give you the airfoil that would generate that. So there's quite a lot of work being done here. A lot of it is using class shape transformations. So they're actually using a representation of the airfoil geometry itself as an input into that surrogate model. And so you'll see that, the work done here and presented here today is a little bit different from that. So it's a bit of a departure from what's commonly done right now in the literature. And I will say there have been a few studies that actually took some of these surrogate models and used them in a rotor optimization process. The thing that I will point out, though, oftentimes using, so that there have been some with ARC2D, there have been some with XFoil, but right, if it's the ARC2D, it still requires extensive computational costs. So they basically run the first module, which does the optimization, or it runs, a lot of data in a CFD solver, and then builds that surrogate model and then plugs that in. So you're still having that very expensive part where you're running all of that two-dimensional CFD. So you're really not, you're saving time, but you're still having a pretty computationally intensive part there. And then, of course, with the XFoil portion, you're just not getting as high of a fidelity as the CFD resolved flow field. Okay, and I do have a point here. So that ARC2D type optimization that I mentioned, that still requires about 3 weeks on a supercomputer. And I believe that work that I'm citing there is just from maybe 1 to 2 years ago, so pretty recently. All right. So let's jump into then the methodology of this work, and starting out with C81 table generation. So I described this kind of at a high level initially. And what I found in a lot of this, actually, this slide really, I would say, kind of was one of the focal points of my dissertation, was that when we're using these hybrid methods where we're setting, say, for example, a BEMT representation or an actuator disk representation of a rotor inside a CFD resolved flow field, we can really gain some accuracy by doing a high discretization of the C81 input decks to model the rotor. So basically, instead of actually resolving the flow field over the true rotor blade geometry, as would be done in bladed resolved CFD, right, we're setting a discretized set of momentum sources inside of that CFD three-dimensional flow field, and then using the C81 lookup tables to impart momentum into the flow field. And so when we do that, if you want to get an accurate solution, you can see the blade that I have here on the right side, which is just an example blade. This is not a Dragonfly blade, but you can see that we have many stations going along the radius of the blade from the root to the tip. And you can tell that the chord is changing, the airfoil that's being used is changing radially. And so if we only use 2 or 3 CD1 decks to describe this entire blade, you'd really be missing some critical information. And then I'll point out as well that if we're using an RPM controlled solution here, so let's say a UAS or something like this, where you're changing RPM as well, these all kind of increase the complexity and really drive you towards a solution where doing a higher discretization of those stations, of those CD1 tables, will lead to giving you a more accurate result there. So in this work, 13 of those radial stations are used to describe the blade and build it into that BEMT module. And in the example I have here, 35 angles of attack, which is really kind of, you could think of that as negative 20 degrees to positive 20 degrees angle of attack. Outside of that, we just fill it in with experimental data. And then 7 Mach numbers, and that's kind of a function of RPM for the application of Dragonfly. And so considering what RPMs our rotors will operate at and then building that into the tables, and the 13 stations. So this results in about 3,200 overflow simulations to build one set of C81 input tables for a rotor. Now think about it, right? For Dragonfly, we have to operate in air because we're going to do some wind tunnel testing here on Earth. We have to simulate it in a Titan environment where it's actually going to fly. And then we also use different test environments. So we have tested at NASA Langley in the Transonic Dynamics Tunnel, which uses R134A, and that's about 75% of the way to Titan's atmospheric density. So just there alone, 3 atmospheres for a single rotor, you're talking about 10,000 overflow simulations in order to properly model one baseline rotor. Now imagine if you want to do rotor optimization and you're looking at hundreds or thousands or millions of potential rotor combinations, it very quickly becomes just a completely intractable number of C81 tables and CFD simulations, even for two-dimensional, that you would need to run in order to do all that. So a lot of performance data is required to support that variable speed rotor design. And especially if you're talking about the optimization side, we really need a faster way to do that. So that brings us to this. This is the Overflow Machine Learning Airfoil Performance Palmo database. So you can see the graphic on the right side. The Dragonfly rotor does use the NACA 4 series airfoils. And so you can see on the right side here a parametrization of those 4 series airfoils in both thickness. So from left to right is varying thickness of the NACA 4 series. And then from bottom to top is varying the camber of those airfoils. And so, the interesting thing, I mentioned a lot of other groups, they use the actual kind of coordinates with the Chebyshev polynomials or Bernstein polynomials for class shape transformations to represent that airfoil in the input space of the surrogate modeling. But here, since the 4 series is fully described, fully parameterized with just 2 values, thickness and camber, we can actually get away with fully representing basically the geometric impact of these airfoils on the resulting CL, CD, and CM using just those 2 input values of thickness and camber. So you can see here the database so far for the 4 series database has 15 of what I call base cubes, where each of these base cubes is running 10 Mach numbers from subsonic to a Mach of 0.9, 8 Reynolds numbers from 75,000 to 8 million, and the angle of attack, like I mentioned, from -20 to 20 degrees. So each of these cubes is about 3,280 simulations, and then those are run for every single one of these airfoils. And so this gives quite a large database here. And kind of the way that I picked these numbers, right, the Mach range, the Reynolds range, really targeting rotorcraft applications where these, even though these are maybe a little bit pushing where we would trust the tool, so 75,000 Reynolds number is low for where you might just trust the overflow and the operation and the way that I'm running it, but it is a comprehensive range of what we might expect to analyze for some UAS or rotorcraft type applications. So we have this initial database of 4 series airfoil thickness and camber, and that's 15 parameterized airfoils, and then 4 additional off-axis airfoils. So you can see these red stars on the image. So that's the NACA 3415, 3418, 4415, and 4421. And those are used for testing. So really the 15 main airfoil cubes we use to train the data, to train the surrogate model. And then these, that's 3,280 times 4. All of that data is held out and withheld for the purposes of testing to make sure that the surrogate model is working well. And so I actually am working the process right now to release all of this data in a NASA TM. So that will be publicly available, this entire data set, which is some very brief example of surrogate modeling and how you might use that in downstream applications. So the hope here is that that is very relevant to rotorcraft analyses. And I will point out as well that so the AIAA Surrogates Modeling TC is planning to use that as an international benchmark so that folks can practice training surrogate models on these large databases and then develop best practices and kind of share knowledge between different groups and things like that with a publicly available problem. I did skip over some overflow data or overflow information of the case setup. So if you're interested, right, 500 periodic cells on the airfoil 2D grid, 600 normal cells, 41 on the trailing edge. So it's a pretty refined grid actually, and doing that, so there's quite refined grid for all of these cases, which is somewhere in the neighborhood of 50 or 60,000 overflow simulations. So let's jump forward then. Now that we talked through that and the airfoil parameterization and everything, let's go into the rotor optimization framework. So this is something that I coded up in Python, and it basically takes that Palmo surrogate model and then plugs it into some scripting that generates the CD1 tables based on a rotor geometry that I want to analyze. And then we plug those CD1 tables into CAMRAD2, and CAMRAD2 is used as the function evaluation. So basically, I'll talk about it more on the next slide, but really coming up with a rotor design and maybe 100 of them simultaneously, and then running them in CAMRAD to analyze them, and then using that to guide the optimization approach, basically. And so CAMRAD2 has been, of course, used extensively for many rotorcraft applications, but notably here for planetary aerial vehicles, it's been used to support Ingenuity for Mars and other Mars-related rotorcraft activities. Now, the rotor optimization script itself has 15 free parameters. So that's trilinear taper, trilinear twist, and bilinear airfoil thickness to chord ratio. So if you really multiply that out, I mean, it's something crazy, like much, much more than 50 million possible rotor combinations. I think that's kind of a very generous number where I've already constrained the problem here. If you really looked at 15 free parameters, it is a humongous design space that is multidimensional, non-convex, and so you would really have kind of the typical optimization approaches would tend to struggle once you get up to this large of a problem. So the initial seeding of the data of the design space is done with the greedy farthest point algorithm. And I'll talk about that a little bit more on the next slide, I believe. And then, of course, optimization strategy, as I mentioned, the Bayesian optimization. So this is an interesting work in that we're simultaneously optimizing the rotor planform and the airfoil out of that 44 series that is being used along the blade. So here's an actual image of the entire framework. And so kind of starting on the left side here, you can see the Palmo database surrogate models, and then that's plugged into the rest of this loop. And so I guess to take a step back, right, this is a Bayesian optimization at a high level is a machine learning based optimization strategy using Bayesian statistics. So what does that really mean? It means that we're going to use a GPR model, that Gaussian process regression that I mentioned earlier on, and use that to explore a humongous amount of this design space. And so you can see I put a note here, it's particularly well suited for quickly finding optimal solutions in this multimodal and non-convex high dimensionality parameter space. So we have a lot of design variables in that rotor design problem, and there would be many local minima if you were to use kind of a more typical approach, maybe something like gradient-based descent or something like this. So you kind of fall into those traps where you maybe converge to a solution, but maybe it's not the global optimum. So Bayesian optimization is actually particularly well suited to find that global optimum. It does use probabilistic GPR surrogate models. So it predicts not only the function of interest, but it also quantifies the uncertainty. So we have this explore, exploit, search parameter where we can simultaneously leverage and build off of the data that we do have. So kind of doing that local optimization, but we can also tell it to explore regions of the design space where we have really high uncertainty. So you're simultaneously moving in the direction that you think is the best, but you're also allowing the optimization to say, hey, this area over here, we really don't know a lot about what's happening there yet. Let's basically go and explore that area and then kind of build from there and continue on. And so the way that that works is using something called the acquisition function. So you can see that on the bottom right side here. And this acquisition function that I use in this work is the expected improvement. So this accounts for both the GPR's prediction of a new rotor performance, for example, but it also accounts for the variance and the uncertainty from the GPR model to come up with an expected improvement value, which you can use to rank one rotor design candidate against another one. And so I'll kind of walk through how the optimization loop works here, and then I think that will put this in a bit better context. So we start out with a seeding of the design space using that greedy farthest point algorithm that I mentioned. So I look at the entire 15-dimensional design space, and I say I want 100 simulations, 100 unique rotors that I'm going to go and analyze in CAMRAD. So I generate those 100 rotors, and I plug them into CAMRAD. Now I will note that, right, in order to do that, I've queried that Palmo surrogate model that I made ahead of time. And so it takes just a few seconds once I decide here are my 100 rotors to basically populate the CD1 tables that are using overflow quality data from that surrogate model. So all of these CAMRAD simulations are nearly as good as if I had run the overflow data directly for all 100 of those unique planform and airfoil combinations. So if you were to do that, that would be a very computationally intensive task. And here, because of the surrogate model, it's almost instantaneous. So then we run those 100 CAMRAD evaluations and get rotor performance for those cases, and then plug that into using a GPR. So I train a GPR, which is, of course, another one of those surrogate models. And then I use that GPR to explore 1 million new rotor designs. So instead of going immediately back to CAMRAD, I use the GPR, which is this reduced order representation of the first 100 CAMRAD simulations, and I use that to estimate or predict the performance of 1 million new randomly generated rotor designs that are in my massive design space. And then we go ahead and use a combination, again, of that greedy FP algorithm with that expected improvement acquisition function that I mentioned. And we use the two of those together to rank those 1 million new rotor designs from top to bottom of most promising to least promising. So then I just skim the top 100 off of the most promising rotor designs. And I have a little bit of logic in there to make sure that, I'm not picking ones that are all just locally right next to each other. So I get a little bit of, design space exploration as well as choosing the ones that seem most promising. And then we go run those again in CAMRAD. So now if I loop back around, I now have 200 CAMRAD evaluations, and I use those 200 to build a better GPR surrogate model, and we repeat this process. So then I train the GPR, use that to analyze 1 million new rotor designs. And so we're simultaneously marching towards an optimal solution, but also improving the accuracy of the GPR model, which could evaluate that entire design space. And so you're buying down the uncertainty while you're simultaneously moving towards an optimal rotor solution. So with that, that's kind of the very technical side of things. Let me talk a little bit about the Dragonfly rotor itself, and then we'll show the results of how that optimization actually marches in time. So for Dragonfly rotor design history, the Phase A rotor was created back around 2016. That's really when the program started. And so a few notes on that one. You can see it has ideal chord and twist distributions, and it used at the time an NACA 6 Series airfoil. So this was kind of the best performance possible without really considering a lot of kind of important factors there, such as structural and other constraints. The Phase B rotor, so we got that one around 2018. And you can see some improvements here, right? Linear chord and thickness, bilinear twist to balance performance over mission profile, some considerations on the airfoil for Reynolds scaling from an air test environment to a TDT, transonic dynamics tunnel test environment to Titan performance, things like benign stall behavior, surface roughness tolerance, since we're not going to be able to clean the rotor blades once they are put on the rocket to Titan, lower chance of condensation in the Titan atmosphere, and things like this. So a lot of different considerations that went into moving towards this 4 Series airfoil, and then really increasing the manufacturability of the rotors. And that's what caused kind of a lot of these design changes on the planform as well. The Phase B star rotor, a little bit more recently, was created to balance kind of torque and blade structural requirements. So we analyzed quite a lot of the vibrations of the entire aircraft and made some adjustments to account for that and to improve the design there. And then working to prevent inboard stall and descent. And then finally, the Phase C rotor was a little bit increased solidity from B star to gain some additional performance and slight twist adjustments for manufacturability. So the Phase C rotor is the baseline that we're looking at in this study today. And on the top right, you can see what was the B star rotor. So we tested this at NASA Langley in that transonic dynamics tunnel. Those are full-scale Dragonfly rotors with the design that we had at that time. And then the bottom right image is the full lander model, so 8 rotors, using some COTS blades, commercial off-the-shelf blades that are not the exact Dragonfly planform, but we would scale their operation so that we would get kind of relative magnitudes of the downwash relative to our flight speeds that we would expect on Titan. So this whole system is about a half scale, and we've actually tested basically the same model with the back shell at NASA Ames in the 80 by 120 foot wind tunnel as well. So for the model that was simulated here and for the design optimization, I mentioned it was one side of the vehicle. So you can see here a representation of Dragonfly with the 4 rotors, 2 coaxial pairs, a front pair and an aft pair. And then just underneath that, this of course isn't CAMRAD, but this is a CFD visualization, just so you can see that the reason we have to model all 4 are that we can often get very large interactional aerodynamics from the front coax to the back coax. And so if you did what is typically done in these optimization studies and just assume a single isolated rotor or a single isolated coaxial rotor, you really won't get the correct optimized rotor solution, right? Because you're ignoring this very major interaction. So this work used 4 rotors and then analyzed it over a range of mission flight conditions. And so we have hover, climb, a cruise, so a forward flight condition, scout, which is a slower cruise condition, and then descent. And so it's a rather complex 4-rotor CAMRAD model with front and aft coaxial rotor systems to capture those interactional aerodynamics. Now this chart here, this shows a little bit of that kind of hop or leapfrog flight that I mentioned. So we start out on the left side here with our lander, and basically the idea is that we know we want to fly to some new destination that we're going to explore, which is this intermediate spot. But before we land there, we're going to overfly it and go to a future landing site of interest, come close to the ground and scout it out. So take some imaging, basically, so that later, after Dragonfly has landed, this information will all be beamed back to Earth, and folks here on the ground can look at those images and pick out a future target landing site. So we overfly the target, image a new landing site of interest, and then backtrack a little bit and land at the original target. So it's kind of like a 2 forward, 1 backward, 2 forward, 1 backward. And so the optimization here, it's looking at that hover, the climb, the cruise, descent condition, scout, which we would do as we're imaging that potential future landing site, And so it's really optimizing over the entire rotor system, those 4 rotors, and the entire mission that we anticipate on Titan. So let's jump into the results here. This slide here looks at the test statistics for the Palmo surrogate model. I really won't spend a lot of time on this one. I mean, basically the kind of takeaway is that the surrogate models we created from that Palmo database performed very well. So for predicting on the amount of data that was held out, so we used we used 95% in this example of the overflow simulations to train that model, and then used 5% of a holdout, which was still 2,000 overflow simulations, to estimate the accuracy of the surrogate model. And you can see here that we're predicting CL, CD, and CM within just a few percent, which, of course, more recently we've been improving those models and getting those numbers down. But for this initial preliminary study, I was quite impressed or quite pleased with that one. So here's an example of the Palmo surrogate model with the black X's on this chart. This is drag coefficient versus angle of attack, compared to overflow, which is the blue line. So that's the actual overflow CFD data. And then the red squares are linear interpolation. And so they all do pretty well, but you can see actually the bottom left corner of the drag bucket here, it does seem that Palmo surrogate model is predicting the airfoil performance a little bit better than linear interpolation over that data set. Now, it does look like they're pretty close, but the caveat here is that the database that we generated for the first round of Palmo was very, very dense. So we have 3,000 simulations for every airfoil. In the future, what we're going to do is coarsen the amount of actual CFD data that we use. And what we anticipate is that the Palmo surrogate model will still perform very well, but linear interpolation will get worse and worse. And so once we coarsen the database, then we expect the surrogate model to significantly outperform that linear interpolation. And I will point out this chart is predicting an airfoil, the NACA 3415, that was not included at all in the training database. So of the predictions you see here, not a single one of the values were included in the training database that generated that surrogate model. So this was a pretty nice result to see that we could do that. So as for the actual rotor optimization, let's talk about that here. And this one is looking at the Bayesian optimization with the explore exploit parameter of 0.05. So I kind of walked you through the process, right? Up here, we start with 100 initial CAMRAD runs. And this chart on the right side is the total mission energy requirement over that leapfrog versus the number of function evaluations. So that's talking about CAMRAD evaluations. So I go ahead and run my 100 CAMRAD simulations, and my best rotor was all the way up here. And then once I get my 100, I run my GPR surrogate model, I train it, and I evaluate it on 1 million new rotor designs. So then we have a discrepancy between the predicted best performing rotor out of that 1 million. And then we go and, we pick the 100 most promising and run them. And then we get the best new rotor performance. And this is an actual CAMRAD evaluation that's that higher current best line, whereas the predicted best is from the GPR model. And so then you can see after doing just one more iteration of that loop, we've almost converged, right? So it continues to reduce that total energy mission requirement a little bit as we continue on, but very rapidly we've gone from the initial baseline case actually and reduced the power requirement, the energy requirement for the mission by quite a substantial amount. So I will point out that top left bullet, the first data point there, that is that phase C rotor. And so a couple of caveats here, right? The optimization very rapidly achieved about a 15% mission power reduction from that baseline. And just to caveat that, so the flight conditions have been updated a little bit since the phase C rotor was designed. And then after we accounted for things like constraints on torque, mean lift coefficient, and blade first flap frequency, so structural, aerodynamic, and other constraints, that improvement would likely be brought back a little bit. But still, it goes to show that this Bayesian optimization framework can achieve probably a 5 to 10% reduction in the total energy requirement over the rotor that we were able to design without using this kind of optimization strategy. Now I think this is kind of the last technical chart that I have here. What I wanted to show was that on the previous slide, I'm going to flash back for just a second here. You see I've circled 3 design points, which all appear to have very similar total mission energy requirement. But if I click forward, these are design candidates 2, 3, and 4. And what I'm plotting here are the rotor chord distributions, twist distributions, and thickness distributions for those 3 unique rotors. And so you see, even though they had very similar power or mission energy requirements, they were all within 0.2% of each other and the global minimum actually. They can be quite different. So design candidate number 2, for example, has a chord. So this solid blue line here has a chord distribution that's really quite small. So it's just up against the lower limit, which probably would be discarded due to structural requirements of the rotor flap frequency. Design candidate number 3, if you look at the orange dash line, has a very high inboard twist. So we would probably discard this solution due to the constraint on mean rotor lift coefficient. And then design candidate 4 actually looks quite good. So even though all 3 of these were output with a near optimal energy requirement for the mission, design candidate 4 is really the only one that would kind of satisfy all the other constraints. So it goes to show that the design space we're working in with 15 input variables on the rotor is very, very large and actually non-convex, right? So we can get multiple near optimal power or energy solutions that can be very different from one another in very diverse regions of that design space. So then the solution here is that we need to apply additional constraints to kind of further tailor and steer the optimization to something that would truly be viable for the mission. So a slide here on summary. Today I talked through the Overflow Machine Learning Airfoil Performance PALMO database and showed that we can use this to efficiently estimate overflow quality data and use that in downstream applications. So that is coming out shortly and will be publicly available, the database at least, with an example or two of how to create surrogate models that can be used in downstream applications. And then secondly, I went through this novel 2-tier machine learning leverage rotor optimization framework. And so looking at optimizing the Dragonfly 4-rotor system, one side of the lander, and using this in a framework coupled with PALMO to do CAMRAD 2 rotor optimization, aerodynamic optimization. And then I kind of walked through and talked about how this greedy farthest point algorithm was used for initial seeding. And then coupling that with Bayesian optimization allowed us to search over 50 million designs. So that chart that I showed previously with about 1,000 CAMRAD evaluations that analyzed something like 50 million designs in that one run. As for conclusions, let's talk a little bit about the numbers. The feed-forward neural networks for the PALMO 4 series database, these were accurate on order of about 1% for the within the linear lift curve slope region and about 3% outside of that. And as I pointed out, it captured the drag bucket a little bit better than linear interpolation. The Bayesian rotor optimization framework identified some candidate improved rotor designs for Dragonfly. And I do point out here, I think before I misspoke a little bit there. So the 900 or so CAMRAD 2 evaluations corresponded to about 10 million GPR evaluations. So we analyzed 10 million kind of rotor designs. And then every time we looked at 1 million, we picked the most promising and ran those in CAMRAD and iterated on this until reaching that converged solution. So for doing that process, 114 CPU cores were used, and that required 5.5 hours for uniform inflow, or about 1 day for prescribed wake in CAMRAD. And so this is really showing you, right, we've done mid-fidelity rotor design optimization in something like, if you did, instead of 114 CPU cores, let's say we ran this on my desktop PC that I have in my office, it would take about 2 to 4 days on my desktop PC. So you're taking what has previously been 3 weeks on a supercomputer and reducing it to what someone could do, to what the practicing engineer could do in a weekend on their office PC. So several candidates that I showed were identified with about 15% lower total mission energy than the baseline. And as I mentioned, right, we have differing planforms. So it kind of shows that once you get up to this really large design space, you get a quite complex design and solution space. And so you need an optimization strategy that's particularly meant to handle that and handle that efficiently while avoiding local minima and things like that. Future work kind of involves applying additional constraints such as the structural, torque limits, mean lift coefficient, and so on. And I do want to leave time for questions. So, I'll just leave this here for a moment. And a lot of folks in my office, of course, my co-author Sven Schmitz at Penn State, all helped me to kind of be able to tie all these different parts of the project together. So yeah, with that, thank you very much for your time, and I'll be happy to take any questions and try to answer them the best I can.
All right, thank you very much, Jason. Wonderful presentation, very interesting stuff. We had one question in the chat asking about the effectiveness metric and where you defined that.
Okay.
How do you define that effectiveness metric? And I think that's the general question.
That's this acquisition function, this one?
Yes, I believe so.
Okay. Yeah, so this one is really just kind of a common acquisition function that's used in Bayesian optimization. So there are a few different ones you could do, expected improvement, and there's a handful of different ones that you could select here depending on your application. So this is just a pretty standard formula. And so this is using the mean predicted value from the GPR model, and then also the variance that the GPR has tied to each mean prediction. So if you imagine then we build the GPR model based off the initial sampling of camera data, and then we use that GPR to evaluate an enormous amount of possible rotor combinations. And at every one of those evaluations, we're getting both a mean value, so let's say a thrust and power, or in this case, let's keep it simple. We're evaluating for all of these 1 million rotors, what is my total mission energy requirement across that entire leapfrog? And so I get one number, that's the energy requirement, and then I also get tied to that number an associated uncertainty value. And so then by plugging that into this equation with that explore exploit parameter that I mentioned, we can kind of guide the optimization to either lean towards optimizing based on the data that we already know, where we believe the best solution lies, or we could turn it in the other direction and tell it to be a little bit more explorative and explore the portions of the design space where from the GPR, we acknowledge that we have very high uncertainty. And so you're kind of betting that even though the prediction there might not be as good, the uncertainty is so large that we might just not realize that there's actually where lies the best solution. And so, yeah, this equation is kind of how you tune that. And I would say it's a bit of trial and error where maybe you do this 2 or 3 times, choosing different values for that explore exploit parameter until you find out what works best for your specific application.
Okay, and I guess the one follow-up is, can you... Oh, sorry, Betty, did you? Oh, I'm having a hard time understanding you, Betty.
Yeah, same for me.
Sorry,
Okay.
that was not me. That is somebody else, and I'm trying to ascertain who that was.
Oh, sorry, I thought that was... Oh, I believe it's Scott. I see his mic lighting up. I don't know if he wanted to ask a question, but I think he's trying to ask a question. I'll ask a follow-up maybe in his stead. Is it possible to steer away that your efficiency function, like by heavily weighting it on explore, exploit, steering it away from known values towards unknown?
I'm sorry. So, yeah, can you please repeat that one?
So you said you basically weight your exploration function to either bias for known predicted values versus your uncertainty values.
Yep.
Is it, if you too heavily weight towards the uncertainty values, will it sort of make it veer off the path into the unknown and ignore the predicted values, or will it still look at those?
Right. Yeah, that's a good question. So the number or that parameter, it could be kind of sensitive depending on how you set it up. But if you pick numbers that are somewhere in the middle, you still allow it to do both of those. So as long as you don't go too extreme on which number you choose, then even if you do kind of bias it towards the exploration, you still have some extent of exploitation. And so even if you kind of tell it, hey, I really want you to design the highly uncertain regions of the design space, it will still use a few out of those 100 new CAMRAD evaluations to kind of optimize based on where we already believe the best solution exists. And so that's part of that benchmarking where you do have to play with it a little bit to make sure that you're using appropriate values for that one. But if you really wanted to, you could turn it into solely being like a optimization based on what we know and completely ignore the regions of high uncertainty. And so then you're very driven in that case by the initial sampling that you've chosen for the first 100 CAMRAD cases in this application. And so that's why it is nice to kind of have it backed a little bit off where it does allow for additional exploration of the design space.
Okay, wonderful. Thank you. I believe that answered Scott's question there. We have
Okay.
another question from Rick asking, what were the rotor design constraints you used and how did you determine them?
Yeah, so the design constraints were somewhat loosely based on how we approach the Dragonfly rotor design. So we have a few things, such as if you notice the Dragonfly rotor is just a rigid, I hesitate to say propeller, but there's no hinges at the root. So there's no flap hinge, there's no lead lag hinge, there's no feathering hinge. And these design considerations were done because it's a cryogenic atmosphere. So you can't just have a bearing, sitting out there in space. If we were to do that, we would have had to figure out some way to have in the rotating frame a heating mechanism and things like this. And so certain aspects of Dragonfly's design were carried over into this optimization study, such as that aspect there. And then things like bounds on the solidity, thrust targets. So for the leapfrog optimization, the rotor was trimmed in every camera iteration to achieve the thrust target that we know we need due to how much Dragonfly weighs, for example. And so a few of these kind of mission metrics were used to constrain the problem while still allowing it to explore a very, very large design space. So with this alone, it analyzed 10 million possible rotor designs in that one day of time. And then as we further constrain this, we're just kind of pushing it towards more and more candidates that would actually be viable and increasing the percentage out of how many we analyze that could potentially be a viable solution for Dragonfly.
All right, thank you. Was there any effort to, if I understand correctly, all the rotors were being optimized for the same blades? Was there any effort to optimize all four independently?
Yeah, that's a good question. So I did not do that. And we actually talked about that early on, whether or not we would allow for, say, upper versus lower rotor differences or front versus aft. And the reason that I did not do that was actually a manufacturability consideration. So if you think about it, let's say that, well, first off, if you allowed for it to change, upper to lower or front to aft, you're kind of exponentially increasing the complexity of your design space, right? Because now not only do you have these 15 design parameters, but you also can have 15 different design parameters and on different rotors within the same simulation. So you make the problem much more computationally intensive, which is surmountable, right? You could do that, but then the downstream effect of, let's say you do choose to go with different rotors, say the upper and lower rotor. If you have, let's say, for example, in a coaxial system, you may want the lower rotor to have a higher twist distribution than the upper rotor, right? Since it's in the downflow, it's in the downwash of the upper rotor in hover. And so normally you would, optimize that rotor a little bit differently with a higher twist so that it would actually perform kind of more evenly. So it would have a similar thrust to the upper rotor in hover. Now, if you lose, let's say you lose the upper rotor, if you have a motor failure during our several year mission on Titan, now you have a lower rotor that was designed to operate in the downwash of the upper, but it's now operating as a single rotor isolated, and it has an entirely too high twist distribution to be operating as a single isolated rotor. So you kind of, you almost shoot yourself in the foot in the failure mode by optimizing to, try and make all four of these rotors as best they can. Then if you have a failure, you actually are kind of in a precarious situation. So we mostly steered clear of that.
Wonderful. We have one more question here. I think we can go over a couple minutes. If
Okay.
people want to hop off, they can. There's nothing keeping you, but we got one here from Dan. Can you give us a feel of some of the bigger insights from the process? What did the algorithm discover that the original designers missed?
Sure. Yeah, let me go back to the slide that has some of the things here. Yeah. I would say that, of course, there was some differences here, right? I mean, the baseline, which is all the way up here, and then these optimized solutions, right? That's a 15% reduction in total mission energy. And so one of the major drivers of this, I would have to say, is that when we designed the rotor originally, although we do consider all of these mission kind of flight trajectories, right? So we're looking at all of these different flight conditions while doing that design. That wasn't the primary driver. So it's not like this energy requirement over the entire mission was not used as the key way to pick the best rotor. And so what you see here, when we allow the optimization to use that as the primary objective, is that, of course, you would get a rotor that's kind of optimized to have that total mission energy minimized. But then the outcome of that, right, is that maybe we get some things that we had previously avoided, such as that high inboard twist, or a really small chord distribution, or whatever the case may be. And so it's kind of different ways to formulate the problem, I guess, really. You know, if in the beginning we said, hey, we really want the rotor to look like this because of best practices, of course, this optimization strategy allows the user or the engineer to explore such a broader range of possibilities than what you would ever be able to do if you're not going to use one of these approaches. And so it does allow us to analyze, you know, millions of more combinations than we would otherwise be able to. So you can search this humongous design space where actually on the design candidate number 2, you see the twist distribution, right, is has this huge kind of drop here on the outboard section. And then the chord distribution, you can see I have a tip taper. So the actual Dragonfly blade, the phase C rotor, does not have this tip taper, but in my optimization, I allowed it to take just the last few percent of the blade and do an aggressive taper. And so little things like that, that because of the computational efficiency of this approach, we're able to build those into this entire process and find designs that, you know, were better, even though this preliminary work wasn't fully constrained. So as I talked through, right, design candidates 2 and 3 would have been discarded for various reasons. But the outlook of this work is that if you apply those constraints, once you apply them in, then you would still find, you know, several design candidates that would have a few percent improvement from the baseline. And then it kind of becomes a question for the larger mission systems engineering problem of whether or not, you know, that delta improvement in performance is worth going back and kind of, you know, changing the rotor, carrying that through, and doing all of the downstream implications of that change.
Okay, and then one last quick little follow-up. So
Okay.
Dan's asking if it was mainly plan form more than airfoil selection in sight.
Yeah, so this one here, we actually restricted the airfoils to be that 4 series since we knew that a future rotor design for the mission would be restricted to that as well. And so although we could have explored, you know, rotors outside of the 4 series, we knew that we wanted it to end up having that. So it was constrained to have that. And so we, you know, we allowed the thickness, which is basically the airfoil degree of freedom that we have. We allowed that to change throughout the optimization. But, you know, a future study, if you weren't looking at Dragonfly, let's say you were just optimizing some other rotor, you could certainly add the airfoil profile itself into that optimization, where not only you're looking at 4 series, but maybe you're looking at, you know, several other company airfoils or NACA 5 series, 6 series, airfoils produced by other governments or industry companies, things like that. You could certainly plug that in here, and that would probably even allow you to get a further enhanced reduction in that mission energy requirement.
Okay, thank you. I know I've got a lot more questions. I'll probably end up emailing you.
Okay,
And
sure.
if you if anyone else has any questions, I believe Jason will be happy to answer those with some emails. I think he had his contact info at the start. But either way, thank you everyone for stopping by. I hope you enjoyed the talk. Look out for more of these in the future. And we'll let everyone go for the day. So thank you very much, Jason.
All right, excellent. Thank you very much. I appreciate everyone joining in.